Okay, as promised, moving on from discussions of waves to discussions of electricity and charge, field and potential. Very tiny personal anecdote. I actually graduated in 1988 from Avondale College, a little college in New South Wales, with a Bachelor of Education with a major in chemistry and a minor in physics. And I'm quite comfortable and happy with both of those. But most of the schools I was in were short of physics teachers, so I ended up teaching a lot more physics than chemistry, getting quite comfortable with that. In 2010, when I was working at the University of Queensland, I went back and did a graduate certificate in science in physics. So just got my science polished up, caught up on some maths that I hadn't used for 20 years and so on. And then when I moved to Griffith in 2012, I started a master's in physics, a Master of Philosophy in Physics. I got about a little under halfway through, so I got confirmation of candidature, and then I became the deputy head of school and had to abandon that master's, which I'm quite disappointed about, but there's only a finite amount of time in the day. I'd love to go back to it at some point, but the focus of my research in that master's was on trapping charged particles. So taking a charged tiny particle like a piece of pollen or some kind of spore or something that's very tiny and being able to levitate it in electric fields. It was quite fascinating work. I could probably tell you more about it another day. But so this kind of work is something that I find very interesting. The ability to maneuver things, objects, with using forces and fields. So talk a little bit about electric charges and fields. So charge basically is just more electrons or less electrons. Like there isn't another vector, for want of a better word, of charge. So the protons obviously are the positive charges, the electrons are the negative, and a substance, obviously if you've got a free proton, which is a hydrogen nucleus with no electrons, so an H+, that's a charge that's not electron related, but it's still the fact that it's got one less electron than a hydrogen atom that makes it be able to carry charge. So an H+ in solution, or I guess in the air, can carry charge. But in general, it's materials that have lost electrons so that they end up having a net positive charge because they have more protons than electrons, or materials that have gained electrons, so they have a net negative charge because they've got more electrons than protons. Charged objects create electric fields, and they exert a force on other charged objects, right? We know, we're going to talk actually at the end of in Module 4, we're going to talk about the 4 fundamental forces. So we know gravity. So anything that has mass exerts a force on anything else that has mass. With charge, anything that has charge exerts a force on anything else that has charge. And then we have the strong and weak nuclear forces, which we might leave on the side of our plate for later. So the field strength, the electric field strength, is just how much force you get for a given amount of charge. So E equals F on Q. The electric field strength measured in newtons per coulomb is the force in newtons divided by the charge in coulombs, right? Which makes sense. The units are consistent and hang together. Coulomb's law, again, you're probably quite familiar with this one. F equals K Q1 Q2 over R squared. The force between two particles with charge 1 and charge 2 is directly proportional to the size of the charges. So they're on the top line. Q1, Q2 are the charges in coulombs. It's inversely proportional to the square of their distance apart, right? So there's an R squared on the bottom line. So if they're twice as far apart, the force is 1/4 as great. If they're 3 times as far apart, the force is 1/9 as great, and so on. It's proportional to the square of the distance. That means it drops off quite quickly, the electric force, right? We know actually that for mass and gravity, there's a very similar equation, which is F equals G m1 m2 over R squared. So also, the force between two masses, directly proportional to the size of the masses, inversely proportional to the square of the distances apart. The constant here, K, is, I've put way too many decimal places there, for all practical purposes, 9 by 10 to the 9. Because if you round 8.9875, right? All of those round up for about 5 decimal places back. So it's 9 by 10 to the 9 for every practical purpose that we're ever going to use it. I just thought that I'd throw that in. That's the Coulomb constant. Kind of interesting. The gravitational constant, G, is from memory 6.67 by 10 to the minus 11. Now look at the relative size of those constants. 10 to the plus 9, 10 to the minus 11. There's 10 to the 20 between them, 20 orders of magnitude between gravitational force and charge and electric force. Now, we experience gravitational force as quite powerful, but that's because we're on a very, very large mass, the Earth, 10 to the 30 kilograms. So we experience quite a lot of gravitational force. But if we had 10 to the 30 coulombs, we would have a vastly greater force. In fact, even a force, so if we have two masses of 1 coulomb each, a meter apart, so Q1 equals 1, Q2 equals 1, R equals 1, then we would have 9 by 10 to the 9 billion newtons of force between those two 1 coulomb charges, right? So the electrical force is very powerful, and a coulomb is quite a big chunk of electricity. We end up using microcoulombs and millicoulombs much more often than full coulombs, because it's that much charge. We seldom get it, and if we did, the forces would be vast. Okay, so Coulomb's law. We can also have an electric potential if we imagine that we have a particular charge, Q, big Q in this case, and we bring another charge, little q, from infinity. We're out here at infinity, and at infinity we say that's the point of zero potential. Remember that for potential energy we get to decide. It's relative. We get to decide our 0 point, and we decide that infinity miles away, infinity kilometers away, infinity meters away is the 0 potential point. So as it comes closer, it's gaining electric potential energy. It's gaining the ability to do work because that's electric potential energy. Now, say big Q is positive and little q is negative. They're going to be attracted. So as little q gets closer, it's got the ability to get attracted more, to have more force to do more work. If they're opposite charges, as we pull it in towards, the electric potential energy is going to be building up. So the work it can do is accelerating this guy back out, right? If we're pushing little q closer and closer to big Q, and they're both repelling, then if we stop pushing and let it go, it'll go back out. So it's got the ability to do work. It's got potential. So the electric potential energy we describe as U, and we can so let's just talk about that. Electrical potential energy, it's the same equation as the Coulomb's law, KQ, Q, but it's over R instead of R squared. It's not an R squared law, it's an R law. So I've done big Q and little q there on the slide, or also Q1 and Q2, because again, it's relative. It doesn't matter which we choose as the central one and which we choose as the one we're bringing towards it, because position in space is relative as well. So that's the electrical potential energy, and then we talk about the electrical potential. So if we don't have a little q, if we don't have a point that we're talking about, sorry, a charge, a second charge, we can still say, well, if we had a charge at that point, it would have that much energy. So we can talk about the potential at that particular point. And the potential is measured in volts. So we can measure the potential in volts of a particular point in space. Now we can also measure the potential in volts of a particular point in an electrical circuit. So if we've got a 5-volt battery in the circuit, then we know that the potential in volts at the positive terminal is +5. The potential in volts at the negative terminal we decide to be 0. The potential in volts at any other point in the circuit, depending where the resistors are and so on, will vary. So we can talk about the electric potential, and we can talk about the electric potential energy of, say, an electron in that circuit. So if I have an electron with a charge of 1.6 by 10 to the minus 19 coulomb that's sitting in my circuit at +5 volts, I can then talk about what's the electric potential energy. What does that energy have the electron to do? It can light a light, or warm a heater, or drive a cathode ray tube or a LCD so that I can watch something, and so on. So it's got potential energy to do something, to do work. For circuits, again, I'm assuming that you're comfortable with Ohm's law, just reminding you of it. V equals IR, or I equals V over R. Again, like everything, you want yourself to be very comfortable with algebra, to be very comfortable with rearranging equations, memorizing one form rather than 4 forms, and then being able to just flip it around in your head to make what you want the subject. And you want your students to be developing that skill. I've been being fairly explicit about the units and why the units make sense and how they hang together. You want to be doing that with your students as well. You want them to understand what a formula means. And I talked about this right at the start, I believe. What does an equation actually mean? Because they need to understand the physics meaning of what's going on. Charge, I've put the little deltas on. Change in charge, current, I, is change in charge over change in time. So coulombs per second. So a current is measured in coulombs per second, but we've created a name for that SI unit, which is the ampere, or the amp for short. So as ever, AMP, ERE, lowercase, capital A for the symbol. V for volts, I for amp, I for current, and A for its units, R for resistance, and omega, the Greek letter capital omega, for its units. So the power in a wire that's carrying a current I, amps, and dropping through a potential difference V is given by P. So P equals VI. So we can actually work out the power in a particular circuit. P equals VI, again, if you memorize V equals IR and P equals VI, you've pretty much got it all, because you can substitute then V equals IR into P equals VI. So I've done that, combining this P equals VI, the power law, for want of a better word, with Ohm's law. So if you substitute IR for V, then you get IR I, or I squared R. So P equals I squared R, P equals V squared over I. I've just subbed in Ohm's law to replace one or other of the two things in that power law. So for example, this is really helpful, because if a transmission line, an overhead transmission line that's carrying electricity from the power station to your house, has a resistance R, then the amount of power wasted, the energy lost as heat, overcoming that resistance in the wire, will be given by P equals I squared R. So what you actually want is to make the current as small as possible. So you want it to have a very high voltage and a very low current in order to get the electricity from the power station to your house without wasting a lot as heat and heating up the wires, which doesn't serve anybody's needs, right? So that's how we know that this power law helps us actually design these systems. And we'll talk a bit in a minute about how you actually achieve that result of having low current, high voltage. We already know from ages ago when we were talking about power, when we talked about work energy and power, I think module 2, power equals work per unit time. So if we combine power equals work per unit time with P equals VI, we end up rearranging it to work equals VI times T. So in other words, the potential difference that's traveling through, the current that's traveling through it, and how long it's doing it for. So the work in joules and the power in watts relate to each other. That's the first tranche of electricity and magnetism. It's been pretty quick, and as I say, a lot of this I can kind of introduce the concepts in the video, but it'll be in the calculations and the examples, applying it to real world situations where it really makes sense. So go ahead and have a look at those example videos that will hopefully explain that a bit more, and do the practice problems, give yourself some practice on them, get comfortable with it, so that if there's any concepts that you're struggling with, more practice, find other examples in other places, ask questions. I've mentioned before, discussion board, email, collaborate sessions. There's lots of avenues that should leave you not feeling confused or lost on any of this stuff.